Thank you very much for joining this session of chemistry. Our lesson today is going to be about the history of the periodic table. So there will be part 1 of periodic table, and then maybe in 2 weeks' time we'll do part 2 of the periodic table. So we want to be able to understand the origins and history of the periodic table. The key vocabulary that we'll be considering are atomic weight, law of octaves, John Newlands, and Dmitry Mendeleev. The last 2 names are names of scientists. On the screen, those who have been watching for quite a bit now, on the screen are 3 images. The first image on your left-hand side is an image of scientists who have grouped together. The second image is just somebody trying to doing his or her best to be able to, arrange the elements that had been discovered at that time. And the final image to your right-hand side is just a cartoon to show the fact that John Newlands was so happy when he was able to determine that there was something called the law of octaves. I'll be commenting on that later. Our learning outcome is very, very simple. I've kept it very simple to make sure that every student understands this lesson. Again, thank you if you're just joining. Make sure you've got your pen or pencil and book or paper that you can do the work on. Whilst the lesson is going on, you may decide to put down some notes because at the end, I'll be asking you some questions. And these notes you write down may come in very handy for you to be able to answer some of the questions in case you miss some of the things that I say. So we are just going to look at the steps in the development of the periodic table as we know it today. So we are going back into the origins. We are going back to the history to look at how all this pan out to give us the periodic table that we've got this time. So I've set prior knowledge here for you. If you can do it, it will take you 1.5 minutes to do it, please. Thank you. Just a quick one. Somebody has a question. So the 2 stands for the atomic number 7, atomic number 17, the atomic number of chlorine. Just to help those who just asked that question. Thank you. I'll add 10 more seconds to the time just to make sure that those who didn't get it can do it. Thank you. Let's have a look at the answers. For helium, there's only 2 electrons, and the first shell takes a maximum of 2 electrons, so the answer is 2. For nitrogen, the atomic number is 7, or the number of protons is 7. The first shell or energy level takes a maximum of 2, and 7 minus 2 gives us 5, so the 5 goes into the outer shell, so the electronic configuration is 2, 5. Remember, the word was write, not draw, so we are just writing it. The final one was chlorine, atomic number 17. The first shell can take a maximum of 2. Second and subsequent shells or energy levels can take a maximum of 8 electrons. We've got 17, so we put 2 in the first shell, and that will be left with 15. You put 8 in the second shell, and you are left with 7. So the 7 goes into the final shell. Just go back again, those who missed the answers. Just 10 seconds, and I'll move on to the next slide again. Thank you. So let's start with the history of the periodic table. So before the discovery of protons, neutrons, and electrons, scientists' first attempts at classifying elements were based on the use of atomic weights of elements. So currently, we no more refer to it as atomic weight. We call it relative atomic mass. And these are the big numbers that you find at the top. If you have your periodic table, you realize that there will be a big number at the top. If you are using a periodic table from the internet, sometimes they write the mass number below it. So for example, if you look at chlorine, it would have 35.5 at the top and 17 at the bottom of the letter Cl. On the internet, sometimes they swap this around. So that's why I'm pointing it out. So it was done using atomic weights of elements. Number 2, the early periodic table was incomplete, and some elements were placed in inappropriate groups if the strict order of atomic weights were followed. By inappropriate, I'm trying to say that they were placed in the wrong groups if the strict order of atomic weights were followed, because that was what they were following at that time. So before John Newlands came in, that was what they were doing. Now, if you look at the screen very carefully, I have placed Newlands octaves on here. Remember, I used the word octaves, and I said during the course of the lesson, I would come back and explain that a bit more. So I've circled 3 elements up there. You can see I've put a red circle around 3 elements: lithium, sodium, and potassium. John Newlands spotted that the properties of elements seemed to repeat every 8 elements when it was placed in order of atomic weight. And because it repeated itself, the 8th element every time, every 8th element, he called it the law of octaves. So the first 3 words there gives you a clue. Oct comes from the word 8. Example, octagon has 8 sides. Octagon is an 8-sided figure, so oct means 8. So what was the success? He had some success with his table. Number 1, he did very well. So you go back to the table and you can see that he was able to place lithium, sodium, and potassium in the same group. And that was an amazing achievement of his. At that time, there were only about 50 elements known, and scientists did not accept his table. There were reasons why his table were not accepted, or the problems. They were because of the problems with the table. First of all, it only worked for the first 20 or so of the known elements. So just first 20 or so elements, it did work for that. Another example of the table or the problems is point 2 here. There were problems. Example, copper was in the same group as lithium, sodium, and potassium. So the question is, why was it a problem to have copper in the same group as lithium, sodium, and potassium? Again, I'll go back to the table. I have circled the elements he put in a particular group, and I've put copper, and I've put a red circle around copper. Excuse me for my rough drawing. I was just doing it by hand. And so there was a problem. He put copper amongst lithium, sodium, and potassium. So what was the problem? Number one was because copper had different properties to these elements. When I mean these elements, sodium, lithium, and potassium. One typical example which you do in year 9 when you do your practicals is reactivity of group 1 elements. You realize that group 1 elements do react with water, and some of them react vigorously. So for example, potassium will react very vigorously with water, but copper does not react with water. So those were some of the things that had to be considered. Copper had a different property to lithium, sodium, and potassium because it couldn't react with water. That table was not the best. Again, it wasn't accepted. So a Russian in 1869 by the name Dmitry Mendeleev came up with a table. You can see on the bottom left-hand side, I've tried to put a cartoon there. You can see Mendeleev thinking way hard, the way we do in class, the way we think about things, the way we arrive at conclusions in science. And that's what Mendeleev is doing. And somebody's trying to tap. And he's so busy trying to think about it. What was wrong with this table? And then it clicked to him. And because of what his work, the Mendeleev's table, which you can see over here, has become the basis for the modern periodic table. What did Mendeleev do? Okay, he also placed the elements in order of atomic weight. But crucially, this is the biggest point which turned the tables, which made his table acceptable. But crucially, he did two things different to Newlands. Number one, Mendeleev left gaps for elements that had not yet been discovered. But amazingly, he had predicted these elements and also predicted the properties of these elements. So if you look at the table, what he did was to leave all these gaps there. At the top, you can see a lot of gaps there. Over here, you can see one more gap there. Number two, he did something against the order of the day. Mendeleev changed the order of the elements slightly in some places based on atomic weight. And if he thought it fitted the properties better, so that's what he was doing. He would change the order of the elements based on the atomic weight. So far as he found it that, oh, this fits, with the properties of the others. So for example, a typical example of what he did was he swapped around the order of iodine. Iodine has atomic weight of 127, and tellurium, which has an atomic weight of 28. What he did was amazing. He placed iodine after tellurium so that it was in the same group as fluorine, chlorine, and bromine, which have similar properties. So if you look at the table very carefully, he puts iodine there. So again, you can see iodine there, placed in group 7. So fluorine, chlorine, bromine, iodine. Amazing, isn't it? Amazing stuff. What happened over the next few years? So after Mendeleev had come out with this idea, number 2, predicted the properties of elements yet to be discovered. When elements with properties were discovered, these were elements that has been predicted by Mendeleev. When they were discovered, they were used to fill the gaps. So for example, gallium 1875 and scandium 1897, germanium in 1886, these were all discovered. And because Mendeleev has already predicted the properties of these elements, he was able to, they were able to put it where it was supposed to be, in the gaps that he's left. Now the biggest thing is here. In each case, the properties of the element closely matched Mendeleev's predictions. This is science. This is science. Knowledge of isotopes made it possible to explain why the order based on atomic weight was not always correct. In other words, when we began to understand isotopes, isotope is an element that has the same number of protons or atomic number, but different number of neutrons. So if they have the same number of protons but different number of neutrons, then the conclusion is that they will have different mass numbers. The relative atomic mass, different mass numbers. And therefore, to get the mass number of that particular atom, we need to find the relative atomic mass. So knowledge of isotopes, number of protons are the same in that element, but the number of neutrons are different. This is what made it possible to explain why the order based on atomic weight was not always correct. Here, I have put the whole lesson into a table just to make sure that you can do it. And also make sure that you have the whole lesson on a PowerPoint, just one slide. So those of you who want to go back to VLE next time to have a look at it, you can just go to this slide and everything that I've talked about will be on just one slide. I want us to see whether we did understand what I talked about. So I'm going to give you a couple of questions for you to do for me. I'll also put the time on screen and I'll leave you to do it. So please, and a big please, just make sure that you got your books, you got your pen. Yep, we are ready to go. Still got about 2.5 minutes. Make sure that you challenge yourself with question 6. So Yusuf from BChem, I'll be answering your question at the end of the lesson. I think I should do it now for you. So an isotope is an element that has the same number of protons, or the atomic number is the same, but different number of neutrons. Okay, I hope that helps you. Same number of protons, but different number of neutrons. So that's for Yusuf from BChem. So we've got 30 seconds. 30 seconds. We've got 10 seconds. Hooray! Time up, time up. What I'm going to do, I'm going to show you the answers. Amazing. I know you've done amazingly well even before I show you the answers. I'll show you the answers, compare the answers to yours. And if you've got any question, yeah, just let me know. So I'll go through the questions. The first one was, in what order were elements classified by scientists' first attempt? The answer is atomic weight. If you write atomic weight, you are correct. If you write atomic weight of elements, you are still correct. That's why I've put that in the bracket. Question 2 was, what is atomic weight known now in modern times? As I mentioned, atomic weight is now referred to as a relative atomic mass. We no more call it atomic weight, so relative atomic mass. Number 3, in what order did Mendeleev put the elements? Again, he put them by their atomic weight. And that was the first thing that he did. 2 ways in which Mendeleev overcame some of the problems with John Newland's table massively. He left gaps for elements that he thought had not been discovered. And the beauty of it, if you go back on the PowerPoint, is that he even predicted the properties of some of the elements that were not yet discovered. And the second one is, in some places, he changed the order of the elements based on atomic weights. That's when he realized that it will fit better with their properties. And so he changed the order. The next question is, why did Mendeleev's ideas become acceptable? And yeah, very simple. He predicted that some new elements will be discovered, as well as predicting their properties. These elements were later discovered, and their properties closely matched his predictions. Amazing. Scientists were so amazed, at how they matched, and that's why his ideas were acceptable compared to John Newland's. The challenge was a very simple question. I wouldn't say very tricky, but you need to understand a few things before you can answer this. So the question was very simple. It says, explain why the knowledge of isotopes made it possible to explain why the order based on atomic weights was not always correct. So the key things we are looking here for is 1, isotopes. Number 2, why did isotopes make it impossible for us to put the periodic table together based only on atomic weights? And all that the examiner was trying to get out of you is for you to write down the definition of an isotope. Because if you look at the definition, I'll read out the answer, and then I'll give you a few explanations to it. Because isotopes have the same number of protons, or if you wrote atomic number, you're still correct, but different number of neutrons. Same number of protons, but different number of neutrons. Please never write but different mass number. If you write that, you are wrong. It is the same number of protons, or you can write the same atomic number but different number of neutrons. That is the only acceptable answer for isotopes. So again, the challenge was just trying to ask you to write down the definition of isotope. You see the way they worded it, the way they worded it. I'll leave the screen on for about 2 minutes for you to do your green pen improvements. Thank you. Thank you, students. I hope by now you finish your green pen improvements. Now, what I would like to do is keep working hard and stay safe. Make sure that you keep safe. Thank you for participating in this lesson. That's the end of the lesson. What will be happening is in the next few days, this will be uploaded to VLE. So if there's any part which was too fast for you, if there's any section that you want to revisit, this lesson again will be available on